Okay, so this is part 2 of our discussion in E126. Part 1 was about electric flux and flux density. And this part 2 will be about chapter 5, which is all about the Gauss's law. This is Gauss's law. Gauss's law was derived from the experiment of Faraday's law, the spherical. And when he discovered that the total flux density coming out from that surface, the sphere, is just equal to the charge inside enclosed. And according to Gauss's law, this is not just limited to uh, a surface that is in spherical. But according to Gauss's law, so this is what it states: the total flux coming out from a closed surface. So the sphere is a closed surface, so it's included, but it's not limited to sphere. Is equal to the net charge enclosed by that surface or within that surface. So in mathematical form, this is the closed integral of the dot product between the flux density and the surface area. And according to Gauss's law, this should be equal to the total or net charge enclosed within. So this is Q enclosed. So this is the integral form of Gauss's law. But before we can apply this one, we need to take some consideration in choosing what surface area or what shape should be used in calculating or applying the Gauss's law. Not all closed surfaces are applicable, but there are it's applicable, but it's harder to deal with. So to make the application of Gauss's law more simpler, we need to take this into consideration. So the first one is, of course, this should be a closed surface. Otherwise, it's not applicable. Number 2, B should be in normal, or perpendicular or tangential or the same direction, tangential to the surface area. So we know that this surface area is a scalar quantity, but we can make it a vector quantity. And we discussed this one in chapter 1, that the surface area can be a vector, and the direction will be the perpendicular direction to the surface area. And if it's normal or tangential at all points of the surface, it should always be in normal or either normal or tangential. It can be both. Some part is normal, some part is tangential. So we need to take that into consideration before we choose the proper surface that we will be using when we apply the Gauss's law. And because this one is in normal or tangential, this is a dot product. So if we recall the definition of a dot product, we multiply the magnitude of the vectors, then we multiply it again with the cosine of the angle between them. So if it's in normal, if D is in normal with DS, it's perpendicular then the cosine of 90 degrees will be equal to 0. But if they are in tangential or the same direction, then the dot product between D and ds will be just equal to D times ds. We just remove the vectors, the direction, because this is a scalar product, and cosine of 0 is 1, so we don't need to put 1 here. So we just take this one. And the third condition here, this should be constant for us to apply the Gauss's law. Otherwise, it's hard to apply Gauss's law. So these are the three conditions we need to fulfill before we apply the Gauss's law. So let's take an example here. If we have a point charge, let's take a point charge Q, positive Q. Let's determine the flux density around distance. Determine the r distance away from the origin or the positive Q charge. So what we do here is we plot it into XYZ axis and we make the origin our positive Q. Now, what will be the best surface area that we will be using here? Can we use a cylindrical surface? Can we use a box or any other? What's the best surface area? So the best surface area is a sphere. Why a sphere? Because if we try to if we try to take a differential area at this sphere here, the direction of that surface area will be perpendicular in that direction. This will be ds, and the direction of d, or the flux density, is the same direction as the field, which is also in outward direction in that direction. So what can we say about the angle between them? So even if we take a surface area at the other part of the surface, it's still in that direction and in that direction. They are always in tangential with each other or in parallel, or they have the same direction. So if we apply the Gauss's law here, Q, the enclosed Q will be equal to the integral of d dot ds. But this time, because they're in tangential, then we can now just make it the we multiply just the magnitude of the two. Now here, usually Q is not given. Sometimes the given is a charge density, or it depends on the type of configuration of the charge. So this one is just a point charge, so we don't have a density here. It's just a point charge, so we just use Q. So to solve for Q, Q will be equal to D times the surface area. So this is the total surface area of the surface that we choose, and the surface that we choose is a sphere. We don't need to integrate this one because we know the surface area of a sphere, and it's equal to 4 pi r squared. So this will be multiplied by 4 pi r squared. Then dividing both sides by 4 pi r squared, we have Q divided by 4 pi r squared. And this will be the magnitude of the flux density at a distance r from the origin, or from Q. So if we want to include the direction, the direction of this one will be outward direction, or ER. So this is the flux density of a point charge with a charge Q. Now, if we divide this one, look at this one. If we divide this one, this whole equation by the permittivity, so D divided by the permittivity, this will be equal to Q all over 4 pi epsilon r squared ER. And this part now here is actually our formula of a point charge formula for electric field. So we can derive the relationship between the flux density and E from this one. So we can now say that D will be equal to the permittivity multiplied by the electric field. And this is a very important concept or relationship between D and E. Why? Because if we can solve for E, we just multiply with the permittivity, then we have already our flux density. And if we also observe this one, they have the same direction. Flux density is in the same direction as the electric field. So if we apply the Gauss's law, you need to know the direction. So if you know the direction of the field, then you know the direction of the flux density. If you want to solve the field, you multiply the permittivity with the flux density, and you have, if you divide it with permittivity, then you have the field. So this is a very important concept, especially when we apply the Gauss's law. So for example, let's take an example here. Before we did derive a very long derivation for an infinitely long, infinite line charge with line charge density rho L. We derived this one before, infinitely long. And it's a tedious derivation. It's a very long derivation because it's infinitely long. But now let's try to solve again this one, but this time using Gauss's law. So the first thing to do is to plot this one into our coordinate system. Let's plot the line charge at the z-axis. So this will be our rho L from negative infinity to positive infinity. And this will be our x and y axis. This is x and this is y. Now, you have to determine the field at this point here. So what will be the direction of the field? We know the direction of the field. It should be outward direction, E, in that direction. So this means that the direction of D is also into that direction. So what will be the best surface that we use in here? We cannot use sphere in this example. Why? Because if we use sphere, E is always going to the right, or in AY direction, or in arrow direction if we use the cylindrical coordinate system. So it's not practical to use the sphere. But what's the practical surface area that we can use? We can use the cylindrical coordinate system. So if we use a cylindrical coordinate system, we use a cylinder surface. So using a cylinder surface, let's try to draw this one here. So if we have a cylinder here, we choose this one as our Gaussian surface, and let's say that this has a length L, and the radius here will be the distance here, which is equal to rho. So this one from here to here is rho, and this is our infinitely long line charge outward. Now we want to determine the flux density at the surface here. So to do that, we need first to determine the direction of our field and the direction of the surfaces. Is it constant? Is it always perpendicular, or is it always in the same direction? So if you take first this one, you take a surface area here at the top, then the direction of our D or surface area will be in upward direction because it should be perpendicular. But the direction of D is the same direction as E. And the direction is either going outward in the direction of rho. So it will be in this direction. This will be our D. So they don't have the same direction, but they are in perpendicular. But if you take another surface area along the lateral surface area of the cylinder here, the direction of the surface will be in this direction, ds. That's true, it's still perpendicular. And also because the direction of the field is arrow, it's outward, it's the same direction as our surface. They have the same direction. And we also have another part here, surface area at this side, at this point, at the bottom. So if you take another surface area, the direction of the surface will be downward, but the direction of the field will be in this direction, still in perpendicular. So we have here three regions. So we need to do the close integral into different regions. We divide them into different regions because they don't have the same direction at all regions, all surfaces. So the Q now here will be equal to the close integral on, let's call this one number 1, number 2 for the lateral area, and number 3 for the bottom. So let's call 1 here. So this will be d dot ds for the top side. Then we add for the second one, number 2, lateral surface area. So number 2 dot ds. And for the last part at the bottom, so this will be d dot ds. And now we can solve the Q. Or before we do that, what Q is not given. The given here is rho L, or the line charge density. What's the relationship between them? We know that rho L is actually equal to dq over dl, or we can simply say that this is q over L. So if we solve for q, q is just equal to rho L times L. So we can substitute this one. So we have rho L times L. This is q, and it should be equal to the integral of that product of the first region. Here, what's the angle between them? The angle between them is 90 degrees. So if you take the cosine of 90, the cosine of 90 is 0. So any number multiplied by 0 is still 0. Then the second part, the lateral area here. So the angle between them is 0. So cosine of 0 is 1. So this is just d, the integral of the surface area. We just take the magnitude because they are in the same direction. And for the last part, the angle between them is again in 90 degrees. So this will also be equal to 0. So the remaining integral will be at the lateral area. And for the lateral area, how do we solve for the total area? Lateral area of a cylinder. So what we do is we expand that cylinder into just like a paper before we foil it. And the area of the lateral area will be this area, and it should be equal to this length times this one. This length here will be equal to the circumference of the circle, which is the circumference, and this one will be L, or the length of the cylinder. So what's the circumference of the cylinder, or a circle? Rho L times L. So this will be equal to d times the surface area. Circumference of a circle is 2 pi times the radius. The radius is rho, so this is rho. This is the circumference, but it's not the area yet, so we need to multiply this one with L, length times width. So we multiply it with L, so that will be the total area of the lateral area. And we can cancel out L now here, and if we solve for d, d will be equal to the line charge density divided by 2 pi rho. And the direction of this one will be in the rho direction, so a rho. So this is our d. So if we solve for e, you just need to divide it by epsilon. So result will be rho L over 2 pi epsilon times r in the rho direction. So we derived this one using a very long derivation before, but now we can derive it again using Gauss's law. Just this solution, it's much simpler compared to our solution. The only disadvantage of this method, this law, is choosing the right surface area. If we choose the right surface area, then everything will be much simpler compared to in our chapter 2. Okay, so we can conclude now that the Gauss's law is a very uh, powerful method in solving electric field or flux density. We can have another example here. Let's take. So this is another example. The volume in cylindrical coordinates between r equals 2 and r equals 4 meters contains a uniform charge density of V. The unit is coulomb per cubic meter. Now we need to determine the flux density at all region. So we try to draw this one. So it's from it's a cylinder r equals 4 and r equals 2. So this will be a hollow cylinder. So we have here the first one. Then r equals 2 inside the cylinder. So it's a hollow cylinder. So the radius of the first one, so if we draw the top view will be just like this. So from here, this is the center. This is 2 meters, and the other one, this is 4 meters. So if you plot this one into the our axis, so this will be our z-axis, and we want to determine the flux density at all regions. So the first region, let's call the inner one region 1. Then between 4 and 2, let's call it region 2. And outside that one, outside that cylinder, let's call it region 3. So we divide it with 3 regions. So for region 1, what will be the flux density at region 1? So inside that one. So is there any enclosed charge? That's the question. Is there any enclosed charge at region 1? Our charges at this point, at this volume here, it's in the same shape of a volume, and it's uniformly distributed with the charge density rho v. So inside this circle, there's no any charge here. So if we use that cylinder using Gauss's law, then if there's no enclosed charge, then d at that region should be equal to that one with the surface area, but still equal to 0 because the Q is equal to 0. Now next, for region 2, this is not equal to 0. So how do we solve this one? So we will be solving from r equals 2 to r equals 4. So we can generalize this one into just equal to r, where r is between, so this one, where r is between from 2 up to 4 meters. So if we do this one now, we can choose to use the surface area of the larger cylinder, the outside one. And to do that, first we need to solve for the enclosed charge. What will be the enclosed charge? Q. So remember, given is rho v. This one, rho v, will be equal to Q divided by So now the volume will be equal to, we can factor out pi here and L. So pi times L, and we have r squared minus 2 squared, which is equal to 4. And if we solve for Q, Q will be equal to pi times rho V times L times r squared minus 4. And we can now use the Gauss law. This should be equal to d dot ds. So what is d dot ds? So again, this is a cylinder. If you remember our previous example, we can neglect the surfaces at the top and the bottom because it will be equal to 0, because the angle between D and DS will be 90 degrees. So we only need to consider the lateral area of the cylinder. And we already know what's the lateral area of the cylinder. It's equal to the circumference times the length. And the circumference is 2 pi r times the length L. So we can now solve for pi rho V L r squared minus 4 will be equal to, so the angle between them is 0, so we just take the magnitude times the total surface area, which is the circumference 2 pi times r, then you multiply it with the length L. Then we can cancel out L here, we can cancel out pi. Then to solve for D, we want to solve for D at this region, region 2, D will be equal to rho V times r squared minus 4 all over 2 times r. So this one all over 2 times r. And the direction of this one, if you consider the direction, we know the direction is outward. It's a cylinder. So it's AR. So this will be the flux density at region 2. And it changes from 2 to 4. Next, for the last region, region 3. So for region 3, now here, we need a surface that will enclose the whole cylinder. So we can choose any shape, or we can choose again cylinder. So we can choose this one if we want. This is our Gaussian surface. Then the enclosed charge will be the total charge. It's not just r squared minus 4, because that will be the total charge from 2 to 4. From this region 2 is from 2 to 4. So every step you need to consider it. But in here, all of them should be inside. So now, our total Q, our total Q now here will be equal to, you can still use that formula, pi rho V times L, but this time this is r squared, 4 squared minus 2 squared. So 4 squared is 16 minus 2 squared minus 4. 16 minus 4 is 12. And so this will be 12 pi rho V times L. That's Q. And this should be equal to the integral now of d dot ds. And again, this is a cylinder, so we know that the other parts of the region up and bottom will be equal to 0. So we need just to consider the lateral area. So this will be 12 pi rho V times L, and this should be equal to d times the integral of the surface area, which is 2 pi times r times L. Then we can cancel out L here. So if we solve for d, d will be equal to cancel out 2 pi. Here we have 6. So 6 times rho v divided by the remaining here is r. And the direction is still in AR direction if we consider the direction. So this will be our flux density outside the uh, whole cylinder. Okay, so one last example before we end this one. Still 30 minutes. Volume charge density is located in free space, as the volume charge density is 2 times e raised to negative 1000 or nanocoulomb per cubic meter for the value of r from 0 to 1 millimeter. And elsewhere, the volume charge density is 0. Now we want to determine the flux density on the surface r equals 1 millimeter. So solution, we don't need to draw this one, we can directly solve this one. First, let us derive the formula for D. So D dot ds is equal to the Q enclosed. And given rho v, we can solve for Q. dq over dv is equal to rho v, or Q is equal to the integral of rho v dv. So this is a volume integral. So we can say that this one is the integral of rho v dv, volume. Then this is a sphere. We can use sphere here because this is a volume charge density. We can enclose that charge density into a sphere. And it's a surface r equals 1 millimeter. So this means it's also a sphere. So now, if it's a sphere, then the angle between the surface area and the flux density will always be the same. And so it should be d times the surface area of the sphere, which will be equal to the circumference 2 pi r times, it's pi r, 4 pi r squared. Wrong. This is wrong. It should be 4 pi r squared. Surface area of a sphere or closed surface sphere. So now for pi r squared. Then this should be equal to rho v dv. And now dv is also, this is a sphere, so we need to use spherical coordinates for this one. So it will be a triple integration. Rho v times dv. Our dv is in spherical coordinate system. If you remember our dv, we derived this one at the first part, chapter 1. So dv is the radius squared times sine theta times dr d theta times d phi. Then the limits for this, for dr, it should be from 0 to 1 millimeter, or this is 0.001. For theta, it should be from 0, not 2 pi. We don't need 1 revolution. We only need from 0 to 5. Then for the phi is from 0, this is 1 revolution, to 2 pi. Then to solve for d now, we just divide this one by 4 pi r squared. Then we can now have our flux density. So d will be equal to the whole thing divided by 4 pi r squared. So before we do that, first we can integrate first before we do that. So how do we integrate this one? It's a triple integration. First, we can integrate the angles before we integrate the radius. Or I substitute the value for rho v first before we integrate. Rho v is 2 e raised to negative 1000 r. So that's rho v times r squared sine theta dr d theta d phi. This is from 0 to 0.001, 0 to pi, and 0 to 2 pi. So we can first integrate d phi because there's no phi in our equation. So it will be, so this will be equal to 0 to 0 0.001, 0 to pi, because we want to solve for the integral of phi. Then we can just take all the r squared sine theta. Then what is remaining will be d phi from 0 to pi, and this will be dr times theta. Then what is the integral of dp? So this one now, this whole thing will be equal to phi. Integral of d phi is phi from 0 to 2 pi. So this is upper limit minus lower limit. So 2 pi minus 0. So this is just equal to 2 pi. And if we multiply it by 2, it will be equal to 4 pi. So we can just remove that one, put it at the first part. Then what will be the next? We can choose the other angle. So other r constant. R here is constant. So r squared and dr. And what is the remaining? We also have e raised to negative 1000 r. 1000 r. So here, the only remaining function will be sine theta and d theta. And this is from 0 to pi. And again, calculating for the integral of this part, integral of sine theta is just negative cosine theta. And if you take the limit from 0 to pi, upper limit minus lower limit, negative cosine of pi minus minus, so plus cosine of 0. Cosine of pi is negative 1, cosine of 0 is 1, so negative 1 times negative 1 is 1. 1 plus 1, this is equal to 2. So the answer here is 2. You multiply it on the outside, it's a constant now, so it will be 4 pi times 2. So 4 pi times 2, this is equal to 8 pi. Then the remaining here will be from 0 to 0 0.001. This is the hardest part, r squared e raised to negative 1000 r dr. To calculate this one, we need IBP, integration by parts. But we can use the shortcut here for IBP. We can use the tabular method, DI method, DI. So derivative and integral. So I choose derivative as r squared here. It will be e raised to negative 1000 r. Then derivative 2r negative 1 over 1000 integral e raised to negative 1000 r. Then take again the derivative here. Derivative of 2r is this r. Then negative 1000 over negative 1000 is 1 over 1000 squared. E raised to negative 1000 r. And lastly, derivative, this should be 2. Derivative 2 is 0. Then this will be negative 1 over 1000 cube. E raised to negative 1000 r. Then multiply, multiply, multiply. Plus, minus, plus. So now the answer here will be, if you take the limit, upper limit minus lower limit, and we multiply them, r squared times 1 over 1000. So this will be 8 pi times negative r squared times e raised to negative 1000 r all over 1000 minus 2r times that one. So 2r e raised to negative 1000 r all over 1000 squared. And lastly, minus 2 e raised to negative 1000 r all over 1000 cube. And the limit is from 0 to 0 0.001. So calculating this one, the result will be equal to 4 times 10 to the negative 9. So this will be equal to 4 times 10 to the negative 9, and this will be nanocoulomb. and this should be equal to d times the area, which is 4 pi r squared, and the radius is I think it's 1 millimeter. It's 1 millimeter, so we need to convert that one into meters. So you multiply it with 0.001 squared. So the unit here will be square millimeter. So D now will be equal to this one divided by this one. So the result will be 3 times 10 to the negative 4. And the unit will be nanocoulomb per square millimeter. So this will be the magnitude of the flux density when R, the surface is R equals 1 millimeter. So this is Gauss's law. So it's easier to use compared to our normal derivation and uh, solutions in chapter 3. So if you master Gauss's law, then you can solve many of the problems that are hard to deal with, as long as you know how to what to use, what surface to use. So okay, so we're done with chapter 5, Gauss's law. See you at the next discussion.